I want to, listen up please, I want to take you guys back through kind of our full journey and kind of get us up to this point, and then we'll push forward through these. And I'm going to save one of these for the end, and it's pretty epic. And then we'll see how it all goes. But several weeks ago, we started doing this, and we started off with the most basic way of determining if a series diverged. And remember, it was the super duper tough coach that would only tell you if you did something wrong. What's the name of that test? Nth term. That's right. Nth term will tell you only divergence. For that reason, some people will just call it the divergence test, because that's what it is. Then we found out about a different coach, a different test for us that was very very fair, but not very versatile. It was very focused on only one type of series. Remember what that second one was? Geometric. Yeah, it only told us anything about geometric series, but it was very fair. It would tell us either way. And then we looked at a series of like 3 tests that were all sort of interrelated. It was the integral test, the P-series test, and harmonic. There was all 3 of those were kind of, oh, she did it again. Oh, wait a minute. Mrs. Skeen, she's doing something about the Founding Fathers. See if I can boot her. And really only good for one type of series, right? And really, and this is similar to the P-series test, like if you can identify that a series is harmonic, you're done, right? It just automatically does what? Diverges, yep. And then we got into some other tests involving series that are a little bit harder to categorize. And these are ones where we had to find another series to help us. What did we call these two? Comparison. 2 different types of comparison. One of them was just a straight up direct comparison, essentially graphically, right? Like which one's above, which one's below, and what's happening. This direct comparison. The other one is the limit comparison. That's where you compare with a limit and a fraction, and you determine the convergence or divergence with that. And then finally, the most recent one was the alternating series test, which was the soccer mom of the group. And the big takeaway there would be that the pluses and the minuses in an alternating series really
don't matter.
No, it's not that they don't matter. They really hurt or help convergence. They really help convergence. They make it much easier. So what an illustration of that would be, if I told you that we had a harmonic series, we would say that the harmonic series does what?
Diverges.
Always diverges. But if you had an alternating harmonic, it always converges. We talked a little bit about absolute and conditional convergence last time, and we finally arrive at the last one. And this is called the ratio test, and this is really useful if you have just like weird combinations, like it's like sort of geometric, but there's other stuff in there. It might have a factorial in there. It might have like 5 or 6 different elements in there. Probably we wouldn't do that many because it would just take too long. Might have a lot of different elements. All of them, you might have like a polynomial and a factorial and a square root and a geometric all combined in some weird way. The ratio test should be able to handle most of those. So here's the ratio test in a nutshell. If you have a series, we're going to call it A sub n. And we run this test. I'll just highlight the test here for you. It's right here. We do the limit as n goes to infinity. Meg, you should be ready to go. And Julie, you guys shouldn't be talking. You should have your notes out because I've just been chatting kind of this whole time. This is the new stuff. So I figure if you're going to ignore me while I'm going over the review, that's your fault. But I'm going to make sure you're paying attention now. So we do this limit as n goes towards infinity. If we wanted to just use like really like unsophisticated terminology, what would you call A sub n plus 1? Like, what is that?
The next term.
It's the next one, right? The next term. And then what would that mean A sub n is? The current one. Yeah, the one we're talking about, and then A sub n plus 1 will be the next one, right? So it's always kind of that pattern here. So we do this limit as n goes towards infinity of the next one over the current one. And if we run that limit and we figure out a value for that, if we get a number that's less than 1, We get a series that converges, absolutely, right? Because we're doing the absolute value here. We're ignoring any pluses and minuses. We're removing them. If we run that exact same limit and we come up with a number that's bigger than 1, and obviously infinity would fit within that bigger than 1 category, then we get a diverging series. But if we run that exact same limit again, we come up with a value, and that value is exactly 1. This would be a time when the ratio test tells us nothing. Probably means we should have picked an earlier test, to be honest with you. We should probably have picked maybe like the limit comparison test or the integral test or whatever it might have been. That would have gotten us home maybe a little bit quicker for sure. Okay, so basically with the ratio test, we're focused on the number 1. This is where there's all kinds of possibilities for confusion, right? Let me just write an example here of what you might get this confused with. What is this? That's the limit comparison, right? Where you've got A sub n is maybe the series you're focusing on, B sub n is some other series you're comparing it to. Now, if I complete this limit and I get, say, like 5, what does that mean?
Oh, it's bigger.
They do the same thing.
Say again?
I said it diverges.
Diverges? Maybe. It's possible.
Converge, but they do the same thing.
That means the A sub n and B sub n are doing the same thing. So do you see where there's potential for confusion? Because in the case of the limit comparison test, if you get a 5, well, that means, okay, well, if A sub n converges, well, so does B sub n. But if you get like a 5 on the ratio test, what does that mean?
It diverges.
Automatically diverge because 5 is bigger than 1. So this ratio test does sort of look similar to the limit comparison test, and so I could see how someone could get them confused. So really focus in on the details here. Let me just put it to you like this. We're going to kind of come full circle back around to this idea of, do you remember way back when? This is even, we talked about this last November, October, something like that. Remember how I showed you how certain series converge and certain series seem to diverge? We did it with those improper integrals. And way back then I said, you know what? It really comes down to how fast are the terms closing in on 0? Or how slow are they closing in on 0? That's what's going to tell us convergence or divergence. And I know it's a little bit weird. Isn't this kind of the heart of that? So if we do this ratio of the next term over the previous term, aren't we sort of measuring the rate at which we're approaching, or the terms are approaching 0? We're saying, is it fast enough? Is it not fast enough? Or is it close enough where we don't know? We should use something else. So that's really what this is getting at. This is relatively algebra heavy, and you guys are all algebra masters. I'm encouraging you. I've seen you be algebra masters before, at least once. So, sir.
So, if I'm just like Williams, right, would this always work?
Doesn't work very well with something. It wouldn't work very well with a P series.
Okay.
Wouldn't work very well with, say, like a harmonic. You'll just get inconclusive. Say again?
Those are you just kind of look at it now.
Totally, yeah. And that's why I said if you get that equals 1 on this one, it probably means that you just jumped right to this, and you probably should have gone back and said, maybe I should just recognize that it's a harmonic. Or maybe it was very easily integrated or something like that. Probably means you skipped something you shouldn't have skipped. Yeah. Okay, so take a look at number 1. So number 1 is obviously a strange combination, right? What's the numerator? What kind of thing is that?
So exponential.
Exponential, you could call it also geometric, right? Denominator is definitely not geometric. It's a factorial. That's the first time we've seen this. Well, no, I won't go there yet. We'll come back around to that. So, if you tried to do this with the nth term test, what would the nth term test tell you here? It would tell you nothing, because doesn't the factorial grow infinitely faster eventually than the exponential? So you'd get a 0, the nth term tells us nothing. Let's run through all of them. It's not geometric. I mean, it's like half geometric, so that wouldn't work. Integration, the integral test with that factorial, no thank you. That would be immediately going on to like graduate level math and all that stuff, like what's the integral? of 1 over the factorial function. Anyways, we'll skip that for the moment. It's clearly not a p-series, obviously not harmonic. It's not alternating. Comparison, we could maybe make this work with comparison, direct comparison, but I would bet it would take us a long time to figure out some function that, I don't know if it would take us a long time, but it would take us longer than we need to take to get there. So comparison maybe would work here. Since it's not alternating, we'd maybe arrive at this ratio test. So I'm trying to get you to think sequentially, like, should I think about the nth term, geometric, integral, et cetera, et cetera, et cetera? We would maybe arrive at this ratio test. I'm thinking that if you were doing this, you would look at that factorial, and you would immediately think, ratio test, it's got a factorial. That's what I'm hoping you would do. All right, so here we go. We're going to go limit as n goes towards infinity. I'm going to do this for you all one time, what I'm about to do here, and I'll show you what I would normally do and encourage you to do what I do. And I'll probably do some erasing here in a second. I need to do the n plus 1th term over the nth term, right? So n plus 1th term, I'm just going to replace all of my n's with n plus 1. So it'll be 2 to the n plus 1 over n plus 1 factorial. So that's my n plus 1th term. And my nth term is just what's already in there. So if you do this right, I think in every case you're going to get a fraction over a fraction. And going back to like algebra 1 or whatever, whenever you've got a fraction over a fraction, what do? You do the copy dot flop thing. So you're not going to catch me writing like this very often. What I will typically do is do that copy dot flop right away. So I'm going to see if I can do some moving around. So I'm going to just move this a little bit, like so. And I'm going to take that 2 to the n over n factorial, and I'm going to erase it from there. And I'm going to now multiply by n factorial over 2 to the n. Okay, so I'm going to always copy dot flop this. You do not have to show that step that I originally showed. Clearly this is equivalent, and this is honestly where I would start. Okay, you all okay with that? So we got to do some simplifying here, I think, to get this to a much easier form to handle. And maybe these two would be the first ones to think about. What's 2 to the n plus 1 over 2 to the n? Right? When you are dividing bases, don't you subtract exponents? So 2 to the n plus 1 minus n, well, the n's would just add out, and you'd get 2. So I've got limit as n goes towards infinity. The numerator is going to be 2 times n factorial over n plus 1 factorial. And I'd like to show you how I think about these. Let's see here. I'm going to go move that up just a little bit. So here's how I like to think about these, and you probably have maybe already thought about this, but I've got to simplify the factorials. And I'm always going to be able to, in this pattern, simplify them. So here is what you could do here. Would you guys agree with me that the denominator is really this? So n plus 1, I'll erase this in a second, but n plus 1 factorial is n plus 1 times n minus 1 dot dot dot, right? Isn't this just n factorial?
Yeah, that makes sense.
And so obviously you'd want to cut things off at the most advantageous place. And so I stopped it at n factorial because I saw that I could then cancel those n factorials out. That's why I stopped it there. I could have kept going a little ways, but there's no good reason to do that. Does that concept make sense as far as breaking that factorial just up a little bit? Okay. All right, so then we do the canceling. And I end up with the limit as n goes towards infinity of 2 over n plus 1. And finally, we can evaluate this limit, and that number is? 0. All right. And 0 is a great number here, but we want to relate it to the ratio test concept here. So what's so important about 0? It's less than 1. That's right. So less than 1. So we can conclude now and say, therefore, that original series does what? Yeah, converges absolutely. Or you could just say converges, perhaps, depending on how the question was worded. Peyton?
Does this not have
No. If it did have pluses and minuses, which you, like, if you got diverging here, then you could put the pluses and minuses back in and reanalyze
Okay.
and see if we get conditional convergence. Yeah. All right. So,
You could probably also, if there was pluses and minuses, you could evaluate that with the alternating circumstances.
exactly, yeah, you'd go back and use that. I agree.
No.
Okay, any questions? Yeah, Aiden, what do you think?
Do you have to state that zero terms, like, as the condition?
Yeah, that's one of those interesting conditions. I don't. I mean, it's one of those things where, like, if I stop to think about why that is, I'd have to really pause and think about that, because I don't know that I've ever seen one like that has, like, some like non-zero, then maybe some zero and non-zero. Because if you did, I would just say, well, let's just cut it off over here, analyze all that stuff, and realize we're adding a finite number to that, which is not going to affect the convergence or divergence. So I think the bottom line is I've never seen anyone ask about that.
Okay.
So, I mean, it is the condition, I suppose, but it's not something I've ever seen, like, made a big deal of. And frankly, I don't see the point. And maybe that's just, I'm not seeing it. But it's maybe worth investigating. Yeah. Beyond the obvious here, like, I probably should say this. If a sub n is 0, you're going to have a problem. To me, that's the obvious reason for the condition. I just don't know if there's a deeper one. Because clearly, you can't just divide by 0 and say, oh, we have a problem if the other terms are non-zero. So, yeah. Okay, so we're gonna skip around a little bit. I can't remember what number. Oh, this is worth doing. Yeah, let's look at number 2. Why don't you guys give number 2 a try? There's no factorials here in number 2, but obviously it's kind of a strange combination of things. So if you would, try this. And I think because of the strange combination of things, it's not geometric, it's not integrable, it's definitely not a p-series, definitely not harmonic, it's not alternating. Comparison's going to be a challenge. For those reasons, I think ratio test would be the way to go.
Yeah, totally ratio.
That's what I was thinking.
You will get a lot of practice with the ratio test a little bit later, a couple sections ahead of us. We're going to come back around and we're going to use the ratio test again for kind of a different purpose. All the concepts will be the same. We're just going to kind of focus in on just the convergence piece, and we'll use it in kind of a different way. So you'll get a lot of good practice with this one.
You got that plus five.
So did you notice how in the end these two kind of overpower the other part?
Yeah,
Right, because you end up with this, right?
right.
You almost could look at this and say, well, wait a minute, isn't that sort of a combination? Right? So, like, long term, you can see how one of them just fades, the other one wins.
Right. So
At
like,
first, it's not very apparent, but
so if we're given multiple choice where it's necessary to use something like this, if I just look at the ratio.
I suppose you could, yeah. It could get a little bit confusing, especially, but I would say, like, I like what you're talking about. I like it as, like, the intuition side of it. Like, in other words, you go into it and you're, like, pretty sure it converges.
Yeah.
Like, I'm feeling like because of this little thing I noticed, I'm pretty sure it converges. So you're almost heading that direction, and you'd be surprised if you got something different and say,
Okay.
oh, what
That'd
if
be
I messed
something.
up? I might have messed, so, something like that.
Okay.
That'd be my advice, just, I would always confirm and make sure, as long as you have time,
Mhm.
but if there's like 30 seconds left and that's the last question, just be like,
So let's just hope we should just go over this.
Yep.
Done.
that'd be a way to like have a wise guess.
Yeah,
You're gonna say it's.
because I guess it
If you were to multiply this together, you got the exponent.
ends up being relatively the same thing with number one, because factorial grows faster. The two ends up not necessarily mattering that much.
So you just
as
get
it's
over.
Yeah, it
just
does,
coefficients.
yeah.
So,
Yep.
I didn't really see that.
I'm gonna set up my original here and we can compare my original ratio.
It's the unsurprised. But I think it, we can do that. What's the?
I actually separated this. And then it's good. Yeah, that's all it's good. Oh, yeah, the revision. That's it, I did not get two. I got 6.
Oh, God.
But 2/3 makes
Rose,
sense.
you're right, I think that's smart.
But I got 6, so,
So when everyone's discussing whether the answer is 1 or 4, you got Abraham Lincoln.
yes.
All right, so I've got my original ratio set up there with the n plus 1th term divided by the nth term. And like I said, I usually just write it in a copy dot flop format. And there's a couple of good simplifications you can do here. Did you all simplify what I have in blue up there? How about in orange? I think both of those could be simplified down and put into a much more helpful format. I would say that they would look like this. Limit as n goes towards infinity. I would have n plus 1 squared times 2 over 3 times n squared.
Oh, I understand my problem now. Dude, wait, I got that right too.
Basically, with the two blue factors, we're going to be subtracting exponents. There's essentially just one extra 2 in the numerator. And with the orange factors, there's an extra 3 in the denominator. So when you do your simplifying, your canceling, whatever you want to call it, you have those leftovers in the appropriate spots.
See, I put the 3 in the
Wait a
numerator.
Wait a second, does that
Gotcha.
mean that if it was 3 to the n minus 1, it wouldn't have worked? Because that 3 wouldn't have been there in the end.
3 to the n minus 1.
Look at this, look at this.
Yeah, because, well, it'd get flipped up. I think that's almost what Peyton did, right? Because if you had 3 to the n
And I think you
over 3 to the n minus 1, you'd get 3 to the n
Isn't it?
feel like somebody said.
minus
No, 'cause if you say.
n plus 1. So you'd get a 3 in the numerator instead of, you have an extra 3 in the numerator. You basically have a 3 to the negative 1 in the denominator, which is really a 3 in the numerator, and you'd get 6.
Right.
So the ratio test would still give us an answer, but it would actually be the opposite answer we're about to get. So yeah, so n plus 1 versus n minus 1 totally makes a difference. I agree. It's just really about that location of where that 3 would be, numerator, denominator. Okay, so I don't know how you guys feel about this. I can show you a couple steps here. Couldn't we rewrite this like this? You okay with that? And then the truth is, 2/3 is just, the absolute value of 2/3 is 2/3, and it's a constant multiple, so really I could take that out if I wanted to. I definitely do not have to do it this way. I just thought I'd show you this way. And now, I suppose I could multiply that n plus 1 quantity squared out, but wouldn't it just be n squared plus blah, blah, blah?
Mm-hmm.
And if I do apply the limit as n goes towards infinity, that limit in my case up there would just be what? It'd be 1, and of course times 2/3 is 2/3. And of course, what's so important about 2/3? It's less than 1. So we can say, therefore, that original series does what? Yeah, that's right. Okay. So I was talking with Logan about this a second ago. Did you see how, really eventually, didn't the geometric part eventually overpower the polynomial part? That 2/3 almost looks sort of like a common ratio sort of deal. And that's really what's going on. Long term, the thing that matters the most here is definitely the geometric part of it. Okay. Any questions, follow-ups there? I want you guys to skip one of them. I want you to skip 3 and go to 4. Skip 3, go to 4.
I was on to something with 3.
So sorry. You might be onto something. I don't know. 3 is pretty intense. Give 4 a shot.
Are you getting confused?
Hey, well, why can't I just do the alternate?
There is a L'Hopital's in number 3.
Oh, where are you skipping?
Wait, on number 3?
There is a L'Hopital's, yeah.
On number 3, can't we just,
Do a what?
do the nth term? Because doesn't that equal infinity?
No, it equals.
Yeah.
I thought 4 was fastest.
Yeah.
It does. I was going to take you through the details of why that works and show you the details behind it, but yeah, your instincts are right on the money.
Okay.
Okay, please try number 4. Please try number 4.
I just don't understand.
Miss Allen,
Brain hurts.
you're what?
Do we have to do this with the ratio, or do this with anything else?
I don't get it.
Number 4?
I'm finishing 3.
I think I want you to try the ratio test on 4.
Can we do both tests at once, where you just say
Why what?
test its own
Do we have
absolute
to
conditionality?
I'm doing it as a proof to figure out why.
So you know how
It's
we
faster.
take out the alternating? You know what, if we put added value in there, is it
There's
just?
no more alternate. I wouldn't even write the alternating.
So we would just do the limit and, n to 1/2 over n plus 1.
Yeah.
That
I think
seems-
Peyton's point is worth everybody thinking about. When you do the ratio test, it's absolute value, so that negative 1 to the n won't even matter. Like, I wouldn't even write it, because you're doing the absolute value, so all those minuses and pluses, they don't
Kill
matter.
yourself.
They're not there anymore.
You're gonna see something.
Just consider the non-alternating part.
This is not gonna be fun.
How's it going?
That's so dumb on 3.
I don't like.
That's why we do
I tried L'Hopital's.
Do it even, like,
It's so dumb.
Why is it so dumb?
Because like the only way you can show this to faster is because it's plus 1. There's like there's nothing you can do because if n's infinite, you can just keep going with L'Hopital's until you're done.
Oh, you need n plus 1 factorial right there.
I cancel it out.
It's more than just a book report. Other than a book report, rather than just a physics equation.
So that plus 1 is plus 1 to the n plus 1 over, okay.
Oh, wait,
Okay, yeah, sure, I can.
See if it works.
Yeah. Cancel out.
You really did say it like that? There's like, that's just so
I'm careful with this notation with the infinity over infinity, shows, if we're gonna do L'Hopital's correctly.
Yes.
I get it. The issue, the thing that I'm like seeing here that's the issue is, if, like this n plus 1 to the n, you treated it like a power rule.
Yeah. Or you can't.
So power rule is explicitly
Oh my God, this
variable
equals one.
based.
What?
Numerical exponent.
Mr. Anderson!
Oh.
That's so stupid.
So we're gonna have to, I would recommend that you rewrite, I would write these two fractions together as one big fraction with an exponent instead of like, because you have n plus 1 to the n, over n to the n. I would write it as n plus 1 over n.
Oh my god!
All to the n.
No,
Okay.
Does that make sense?
Yeah.
I would write it like
Oh,
that.
I got you.
So instead of, it's so much easier for me to do than I show you. So instead of this, I would write it like this.
It says to do the ratio.
There's
test.
still some hard things to go here because doing the derivative of that, not gonna
Why are we
happen.
doing the derivative of that?
He's working on number 3.
Yeah.
I'll give you a hint. Natural logs are the key. Natural logs.
Wait, that's the.
Whenever you have issues with exponents, which clearly we have issues with exponents,
Yeah.
logarithms.
Isn't it n plus one squared though?
I did a ratio test, and gave me 1.
Yes.
How did you
So
get
you should
one?
get-
So you do it all for nothing?
Mr. Anderson, I don't even know how to get one.
No, but if.
Hang on.
Wait,
I'm
So, hey,
bad
let's-
at that.
Sam, you're being very short-sighted here. I'll explain why I had you do this in a second. Let's see. Here's the setup. We'd go limit as n goes towards infinity of root n plus 1 over n plus 2, right? N plus 1 times n plus 1 over root n. Just my first step there with my correct ratio and my limit of that. And this could be a point where you would say, well, gosh, this is such a mess. How am I supposed to handle this? Here's a couple ways you could handle it. A small rewrite like this would be like root n plus 1 over root n times n plus 1 over n plus 2. Just a very small rearrangement, right? And then do you remember that as long as the limits exist, the limit of a product is equal to the product of two limits.
Wait, can you say that again?
As long as the limits exist, then if you have the limit of a product, which is what we have, then you could rewrite it as the product of two individual limits. So it would be the limit as n goes towards infinity of this.
Why did you switch them? Why can you switch them? What?
That's allowed. They're all being multiplied together. It don't matter where they are.
Switch what?
That's insane.
What did I?
Yeah, the order doesn't matter with multiplication, so I just basically swap those two.
Fake math. It's okay.
I just, like I said, it's basically like, are you going to do 1/2 times 2/3
Fake math.
or 1/3 times 1? 1/3 times 2 halves. You can like,
Yeah, is that on the wall here somewhere?
no, I'm just making something up.
That's on the wall somewhere.
Wait, what?
Oh, yeah, the commutative property. Yeah, commutative property of multiplication right there. It is on the wall.
I can't believe that just came back to bite.
You better let those Algebra 1 kids know that.
This is
actually-
important.
It might keep coming back. It might actually help your thinking.
Literally, I had to ask a question about it.
I'll say, like, I've got this BC student, and he was like, what's that thing called? What can you do when you switch? Can you even switch? Yes, you can switch. Anyways,
How can you see it? Doesn't even know how to do algebra.
so are you guys okay with that? And maybe I should do one more rewrite. Are you guys okay with this? If I took this first one and wrote all of this?
Yeah.
Oh, I didn't even think you needed to do that.
Yeah, I don't think you have to either. I just thought
So
maybe,
wouldn't that just be 1 times 1?
yes, totally agree. I'm just trying to show you lots of little detailed steps. To be perfectly honest with you, if you looked at this right here, this first step, and you just said, hey, that equals 1, I'm totally okay with that. I mean, I think you can actually, isn't the degree of the numerator 3/2?
Yep.
Degree of the denominator is 3/2. There's a bunch of other little details in there. And the lead
It's the
coefficients are
highest
both
degree.
1.
Yeah, the same.
So
Very
this,
fair.
you could take it all the way through to here and get 1 times 1 equals 1, or you could have just at the very start said, hey, look, it's the pre-calc trick. Lead coefficient ratio is 1.
Yeah,
So,
lovely.
okay, so
What's the point?
Oh, I totally.
listen, please. So this number 1, this means the ratio test tells us nothing.
It does.
So Sam is like, so we did all that for nothing. He's super upset. I wanted to do this for a couple reasons. The main reason is, think of it backwards. Let's say you had some tests later on, some quiz later on, and we never talked about this, and you get equals 1. Conceivably, someone could get upset and say, wait a minute, we never even talked about that. We never even saw that in class. I shouldn't be required to know this. So I'm letting you know this is what it might look like, right? You with me? And also from the perspective of, like I mentioned earlier, if you do get this, it probably means that you skipped something, one of those earlier tests that you probably should have used, right? So
Alternating series.
an alternating series test would be very wise here because namely it's an alternating series, and I think it's going to help us, right? So you might have skipped over the alternating series test. Let's go ahead and do it. So I'm going to say this is an alternating series, and what's the limit as n goes towards infinity of the non-alternating part?
What?
As n goes towards infinity, it would be approaching 0, right? It would be the degree trick from pre-calc, right? Degree of numerator 1/2, degree of denominator 1, or you could do a L'Hopital's rule or something along those lines. Or you could do some division. I prefer the whole pre-calc trick, to be honest. We get 0, and if a sub n equals this, then a sub n plus 1 is less than or equal to a sub n on the interval. And let's see here, is that going to apply from 1 to infinity? It'd be 1/2.
Yes.
It'd be, yeah, I think starting right away, right? Because that square root really slows the growth of the top. So yeah, I think we probably could say from 1 to infinity. Therefore, by the alternating series test, the series converges. So again, 2 reasons why we use the ratio test here. Number 1, to show you that sometimes you could get 1. And then if you do get 1, what do you do besides freaking out and crying in the corner? No, you don't do that.
I absolutely.
You find an earlier test, one that we've talked about in the past, that probably would have worked better. In this case, it was the alternating series test. If you tried the ratio test with a harmonic series, you're going to get 1. And you're going to say, what? This didn't work. Oh, it's harmonic. I should have just done that. So I want to help you with this just so there's less panic if this happens. Okay, how we doing? All right, so I want to take you on this this final journey with the ratio test here. It's number 3, and show you how this works. I would say, just guys, full disclosure, this is probably something that probably beyond what I would assess you on. I kind of threw this in here as an enrichment problem, they like to call these. Do you think you could maybe do this? Because it's a pretty tough one. So here we go. Limit as n goes towards infinity. I'll tell you, the setup is actually really easy, right? It's the stuff that comes later. So this would be n plus 1 to the n plus 1 over n plus 1 factorial, so on and so forth. I've got my ratio. I'm feeling good.
This looks bizarre.
It's a tough one. It is a tough one. Would you guys be okay if I canceled this with this and got limit as n goes towards infinity, and it would be n plus 1 to the n plus 1 over n plus 1 times n to the n? And that's really that exact same pattern we had earlier in class with the factorials. Okay, so now, what could I do? Well, maybe I could work with the top and get limit as n goes towards infinity. Wouldn't the top be n plus 1 to the n times n plus 1 to the 1? So that old exponent, speaking of what Jack said earlier with the old Algebra 1 rules, some of these old exponent rules coming back into play here, right? So this would cancel with this. And I'm going to do a minor rewrite while I'm coming back up here. I'm going to say that this is limit as n goes towards infinity. And I'm going to write this as n plus 1 over n, all to the nth power. Right, it's n plus 1 to the n over n to the n. Sorry.
Why? We can't use the power rule with variable exponents?
It just doesn't work. I mean, we could go through and prove it rigorously, but you can try it out. It just doesn't work, like numerically speaking. To me, what I would do if I were you is I would graph n to the n,
Okay.
and then notice the pattern of the slopes and see if you can match it with the power rule,
Okay.
and you'd see that the numbers just are different.
Okay.
Yeah. Yeah, you end up with some pretty crazy stuff.
Really?
Yeah. trying to do the derivative of like n to the n or n factorial. Some of the functions that end up coming up actually have names like the zeta function, the beta function, the gamma function. Some pretty crazy stuff. They're cool, but beyond the scope of our class for sure. Yeah.
I know, but
Right.
still,
Meg, what are you
the test
thinking?
is telling you that-
The end test, yeah.
but this is equals one, and
It was a divergence.
Oh, yeah. Once you get it like here, are you allowed to just like do the end test since it's like in that form?
Nth term test.
In that form.
Well, that's not the series anymore.
Right, that's why I don't.
Yeah, I don't think we can say
But it's
this is
gonna
the new
equal one,
series.
So
Say,
it's not gonna work.
say again?
This isn't gonna work,
Why not?
right?
Because it equals 1.
But it's
Get
gonna
to the
equal
end term
one.
because that's.
Well-
Over infinity is one,
Oh, this is so lovely. This is where we're going. So, great analysis. So if I do this, I'm not going to write equals because that would be incorrect. Wouldn't I, like, isn't the limit as n goes towards infinity of n plus 1 over n, isn't that just 1?
Yeah.
And so Meg's saying, hey, it's 1 to the infinity. And I agree with you, but then you took it one step too far. You said, and that I disagree with.
What?
So,
There's one times one times
Hey.
one times
listen now. I hinted at this before. You got to hear me out. You need to have an open mind. If I said 1 to the infinity, doesn't that mean 1 times 1 times 1
Right,
times
right.
1 times 1 forever? The minute you stop and say, and that equals 1, you know what you're not doing?
Oh, it's the limit as one to infinity.
Right.
equals
What you're not doing is you're not doing what it's telling you to do. Because it says you have to do it forever. You stopped. So you're not actually doing what it told you to do.
So could we say,
So you're going to find something interesting out with this. Yeah.
Could we say the limit of one to infinity is equal
What
to
to the
1?
end.
Well, so if you said limit as x goes towards infinity of 1 to the x, maybe that would be a little bit different, but that's not exactly what this is, right? There's all these little fractiony things that get added in there,
No.
right?
No.
That's not the same. Okay, so, oh yes, Aiden, I'm sorry, go ahead.
Can you say, well, can you make the conclusion from, you can say on the interval from 1 to infinity that I know n plus 1 over n is always going to be greater than 1, and you can basically call it a geometric series.
Oh, it's not though. A geometric series has a numerical base.
Wouldn't it, will it be effective for numerical?
You're almost doing like a comparison idea, right? Sort of a comparison idea, but we're well into this ratio test. We can't shift gears and say, and now we'll do the geometric or the geometric series test on this thing that's not really the series, right? So I'll show this to you. I would not expect you just to come up with this. Like I said, somebody would probably call this an enrichment question because it's beyond where we've been, and it's probably beyond where I'd expect you just to be. Of course, perfect, make perfect sense. So if you get this 1 to the infinity thing, that actually is going to end up leading us to a L'Hopital's rule eventually. I want to show you how this works. You might look at this and say, how would I be expected to know? Hey, listen, you might look at this and say, how on earth would I be expected to know this? The answer is, I don't think I would expect you to know this. So I'm just showing it to you, just for fun. Just for fun.
Wait, so this is not something we'd be testing?
No. So check this out. I'm going to set this up as an equation now. This will allow us to use logarithms. And the other thing I'm going to do here is I'm going to drop the absolute values. I'm going to actually evaluate them, and here's why. If n starts at 1 and goes up, is there any way that n plus 1 over n to the n could be negative? So I know that the absolute value of this could be positive. So it'll be n plus 1 to the over n to the n. So guys, here's step 1. This is a little more advanced. It's not beyond you, just kind of some unexpected steps. I'm going to do the natural log of both sides. And here's my way of thinking about this. If I've got a problem with an exponent, which to me 1 to the infinity has a problem with an exponent, I'm going to use logarithms, right? Logarithms help us with exponents. Here's what it would look like next. Natural, oh, you said wait. And I'm waiting.
Well, never mind, keep going.
Doesn't have to be a log base since there's no e's.
That's what I was gonna lock it.
I'm going to use e's because e's are very convenient. I could use log base 10, that's just less convenient.
Okay.
I could use basically any log base that I want. So I'm using e's. So do you see what I just did there?
Oh, wow.
Little log property?
No, I said aloud.
What rule am I breaking?
Not my head.
Your head. Okay.
Wait a minute.
Walk me
No.
through that.
How am I ever gonna know this?
Hey guys, hey, let me say this. The one thing that doesn't work, one thing that doesn't work is when you all talk at the same time. So if you have a question, hey,
Explain yourself.
guys, it doesn't work when you all talk at the same time. So Logan said, can we explain that? This would be your old log property from back in pre-calc. If you have natural log of x to the a, that equals a times natural log of x. And so I've just taken this n, and I've used that log property and dropped it down in front.
Oh, yeah.
So, do you guys remember how L'Hopital's rule needs to be basically like an infinity for the top limit and an infinity for the bottom limit? So, or a 0 and a 0, right? It's got to be a fraction. So this might break your head again, and if it does, I'm very sorry. I'm not trying to do that. Check this out. Couldn't I do one more small rewrite
Oh, yep.
and write it as this?
Yes.
Isn't multiplication by n the exact same thing as division by 1 over n? It's a copy dot flop. I am just for sake of time going to kind of break my own rule here. Isn't this a 0 and a 0 now? Wouldn't I get natural log of 1 over 0, which is just 0 over 0? All right, I'm going to switch colors just so you can see it. We're actually almost done. So I'm going to say natural log of y equals, limit as n goes towards infinity. So the derivative of the numerator would be 1 over n plus 1 over n times, oh gosh, can I make I want to make this a little bit easier on you. Let me just do a small rewrite. Are you okay with n plus 1 over n being 1 plus 1 over n? If I just do some canceling?
Yep.
You okay with that? Okay, so here we go. So it'd be 1 over 1 plus 1 over n times the derivative. Well, the derivative of 1 is 0. The derivative of 1 over n is actually this. The derivative of 1 over n is still this. So there's your cancellation. Check this out.
That's that cool.
So now as you apply the limit to the leftovers, what do you get?
1.
So then remember that originally I set up y to equal the limit that I wanted, right? So if ln of y equals 1, what does y equal? No, it equals e to the 1, which is e. And what's so important about e? It's bigger than 1.
Oh my gosh.
Therefore, the series diverges and we're done.
How long did it take you to figure that out?
10 minutes.
I don't know if I ever timed myself. It's been a long time since I did anything like this, like for the first time. So I honestly don't remember the very first time I did something like this. But if you have to show analysis, you have to do this. If your reason is, I know this rankings thing,
I know the rankings.
right? But no one's going to take that as evidence that you actually are a master of this.
You can say that n to the n on the interval from 1 to infinity is always greater than a factorial. Why not?
Both my parents majored in biology.
On some interval, so you could maybe do a comparison, right? You probably could do a comparison.
So you could say that the interval, you could say that on the interval from 2 to infinity, n to the n.
Have a good weekend, you guys.
Oh, you can just say that on the interval from 1 to infinity, n to the n is greater than or equal to
Thank you, guys. Have a great weekend.
factorial.
Yeah.
Which means that
Yeah, the comparison would be tough. You probably could find one though. There's definitely ways. I imagine there's ways around it. Probably comparison.